Hello all, welcome to the 18th episode of Deep Learning with Pytorch series. So this would be a quick run through of a coding session where we will talk about how we can use the nn.Sequential for building a neural network model, which is much more easier to do while comparing with the OOPS concept based model, which we have been using so far, right? So this nn.Sequential is quite similar to what how we used to build model in Keras previously. And apart from that, I also wanted to show you how to build a model, which is kind of a device agnostic model, which can work either in CPU and GPU. Based on the GPU availability, it can switch to a GPU based modeling approach, or if there is not availability of GPU, it can still run on a CPU code on a CPU machine, right? And also in the end, we will talk about how to save and load a PyTorch model, right? So yeah, let's get started. So these are like very basic stuff which we have gone through multiple times. So I will just skip this. So we are still doing the multi-class classification using MNIST, and we will see these concepts which I mentioned using this MNIST data set itself. So till now, it's all remains same. We use a batch size of 50 and we create a train loader. Then we check the size of my batch, a particular batch, which is like 50 number of training examples are there, and also a corresponding 50 labels, target labels are there. Then here, the new concept which I wanted to discuss here is using this nn.Sequential, you can build a model in a much more simpler way. Here you just mention nn.Sequential, then you start building your fully connected layer, which accepts the input parameter as 784. Like these are the features which are available in the input data, and then we have 512 nodes in a first hidden layer. Then we use a activation function, which is relu. We also use a dropout here with a value of zero point 0.3. And then we have another fully connected layer, and we have a dropout layer also here where we have changed the value of the probability. Here we are using a higher probability, so you can see like for different layers we can use a different value of dropout, and with that we can build a model using this simple technique of nn.Sequential, right? Then we define our usual loss function, the optimizer with the learning rate, and also we pass the model parameters in the stochastic gradient descent optimizer, right? Then the second thing which I wanted to show in this video was like you can build a device agnostic code based on the availability of GPU, or if there is not availability of GPU, the same code can still run in a CPU based machine, right? So at first you can check if this torch.cuda dot is available is what is the value of this, right? So if there is a available GPU, it will give you the value as true, else false. So I'm running in my local machine, so where I do not have a GPU, so it shows you that the value is false, right? Now we can create a model agnostic code where we will, based on the availability of the GPU, we can write kind of a if else condition, and it will give you the device for which your code is running, right? So we check if there is any CUDA available or not. If that is available, we mention the device as CUDA, else we mention the torch.device as CPU, right? So here you will see like the output is CPU, right? Then the first thing we need to do is you need to move your model to a particular device, the device on which your code is running, right? So whether it's a GPU or a CPU, you need to move your model to that particular device. So model.to, and you pass the device as a parameter to this function, and in using this, you will kind of move your model to the particular device on which your code is kind of running. Then you write your training code or the training epoch, where you introduce two new things, that you also need to move your data and target to the device on which you are working on. So this will move your data and target input and level tensors to the available device, right? So once that is done, the rest of the things are same as we have seen in the previous coding sessions. Then you monitor your loss. Then with that, your model will be trained in a code which is model agnostic, which does not depend whether you are running on a CPU or GPU. Based on that, it can adopt your system on which you are running the code, right? Now, the last thing which I wanted to talk in this short video is how we can save and load the model. So here we can print our model. So we will see like all the layers of my models are coming up here, right? So the linear layer, the dropout layer, the activation functions, all with the values of your number of nodes in each of these hidden layers are also being shown here, right? So once that is done, you can also see the weights and biases of your model, right? So how we do that? You use this model.StateDict, and then you access the keys of this state dict. With that, you can access each of the weights and biases associated with the different layers, different hidden layers of your neural network, right? So this is how the output looks like. And once you have accessed those things, you can also print those values, and we can also access the weights and biases values. So if you want to, for any downstream task, you need to access the weights and bias values. This is the way to do it. You will run through a loop on your state dict, and you will access using dot items, which will return a dictionary of params and values, and for each param you will have a corresponding values. So for like this example, for 0th weight, which is associated, the weight associated with first hidden layer, we can see the corresponding value of that weight parameter, right? Now after that, you can, once you have like understood how the inner mechanism is working, where the weights and biases are stored and how you can access that, then using this state dict, you can save your model, right? So to save your model, the function is torch.save, where you need to mention what is your state dict and also the name of your saved model, right? So the name which we are using here is model.pth. So this pth is the extension that we generally use in case of storing a Pytorch model, right? So once you save it, once your model is trained, then you can save it. At later point of time, you can load that model and start doing the inference using that model, right? So you can just load the state dict. So using this state dict, you can also print the keys, and with the model, which the once you build the model architecture, you can load the weights and biases from your state dict to the model, right? So your model is which you build, the model architecture which you have, that should have the same architecture of the previously trained saved model, where we have the state dicts and the corresponding weights and biases associated with. So that's the thing you need to keep in mind while loading the state dict. It will only work if the new model architecture is exactly same as the saved models architecture, right? So once you like write down the model code or the model architecture, then you can load the weights and biases from your saved model, and you don't need to train your model again. And using this code, you can now start making inferences on a new data set, right? So yeah, that's all I wanted to talk in this short video. So in the next video, we will try to see, apart from using GPU, so you using GPU, you generally use GPU to fasten your training process, right? Your training process will be much more optimized, and it will run on the GPU, where the matrix multiplications will happen much more quickly. Your training time will be reduced. But there are a few other techniques through which you can also speed up your neural network training process. So that I will talk in detail in the next video. So thank you all. Thanks for your time. And if you like this video, please please subscribe this channels if you haven't, and also like and share this video with your friends and colleagues. Thank you. Thanks for your time.